Today we're talking about experimental and theoretical probability. Someone raise your hand and tell me, what comes to your mind when I say experimental? What do you think of? Raise your hand. Okay, what do you think of when you hear the word experimental? Isla?
You can do like experiment.
Okay, you can do. Doing, okay? So experimental requires action. Like the mad scientists, has anybody ever seen like those TV shows where like their lab blows up and that type of thing? They're experimenting, okay? So theoretical. Theoretical, has anybody ever said to you, well, in theory, this is what should happen? What does that mean? It means on paper, in a perfect world scenario, this is what should happen. So the main difference between the two is that experimental probability is reality. That's reality. Theoretical probability is your hypothetical, or what should happen. We calculate them both the same way, but you do need to understand the difference between the two. All right? And we're going to explore more actually how they are connected, as far as their percentages. We'll explore that more later in the lesson. All right, so here's your formula. Did I write it in for you? Oh, how nice of me. Okay, just kidding. All right, so the probability of an event happening. What is your targeted outcome? The probability of rolling a 5, okay? Well, I would write rolling a 5 down here in parentheses. You're going to see me writing that. That just shows your reader that you know what your targeted outcome is the number of times the event occurs divided by the total number of trials. You actually did it, okay? All right, so here we go. Example 1. The table shows the results of spinning a penny 25 times. What is the experimental probability of spinning heads? All right, so look at the table. All right. And then I want to give you the theoretical scenario. So, in theory, all right, how many possible outcomes, are you paying attention? How many possible outcomes are there?
25.
No, in theory. There's only 2, heads or tails, right? So I would say, in theory, there's a 50-50 shot, right, of either getting heads or tails. That's theoretical. However, when I look at this table of values, is it a 50-50 split? No, and if I were to spin it 25 times again, would I have the same exact numbers again?
No.
I would have different numbers, all right? So experimental probability really is just what ends up happening, and it's almost the luck of the draw, right? Okay? But in theory, it should be 50-50. So you see the difference kind of already. All right, so let's calculate the experimental probability. The probability that I would spin a what? Heads. So the probability of heads, remember what goes in parentheses is my targeted outcome. So how many times did I spin heads? 6 out of how many total tries? 25. All right, so I need you to put this part on your homework. If you don't put the beginning part, if all you put is a fraction, you will lose points on homework, on a quiz, on a test. That targeted outcome needs to be mentioned. Okay, so now 6 out of 25, I would need to convert that to a percentage. I know that I can do that by dividing 6 divided by 25, and I get 0.24. But is that a percentage? No, what would be my percentage? 24%. Okay. Now, what did I say was the theoretical probability? What did I say it was going to be? It's going to be 50-50. Would you agree that the experimental, when I actually did the experiment, it was far from 50-50, wasn't it? Okay? So I'm going to talk more about this in a minute, but I just want to kind of plant this thought in your head. All right? Experimental probability, when it's basically not very many tries, 25 times spinning it is not very many, okay? There's going to be a pretty big gap, but what we see happen is if I had, say, spun this penny 300 times, if I had increased the number of trials, what the data shows is as I increase the number of trials, that probability starts matching up between your experimental and your theoretical. Okay? All right, and I'll explain more as we kind of get along. But basically, if I don't have a lot of trials, I could see this kind of vary quite a bit from the theoretical probability. So let's look at another one. Okay, so this table shows the results of rolling a number cube 50 times. Find the experimental probability of the following two scenarios: rolling a 3 and rolling an odd number. All right, so remember, we start off by saying probability that I roll a 3. All right, so what is my targeted outcome? That's what I write in parentheses. And now I need favorable out of total. Favorable out of total. Okay, so how many times did I roll a 3 according to the table? 8. Okay. And how many times total? 50. Now, what if the problem had not told me 50? What if you didn't know that? Is there, what did you say? You'd add them all together, okay? So if it didn't tell you, you could still add all the frequencies together and it should be 50. Okay? All right, so now how could I convert that to a percentage? 8 over 50. You divide, 8 divided by 50. And then in your calculator, you see a decimal value. Could you go ahead and change that to a percentage? Yeah. So what's it going to be as a percentage? 16%. All right, so I'm going to pause for a minute. I'm going to see, just let you guys get started on this. You might be stuck right away on it, and that's okay. All right, but you might be able to kind of figure out what to do here. All right, so probability of rolling an odd number. Remember what you're supposed to write before the equal sign. Okay, so something goes here, and then equals, and then I'd have a fraction over here. All right, that's what I'm saying. It's hard to walk around and check all of y'all's, so that's why I'm really emphasizing you need to put your targeted outcome in parentheses. All right, that is important because that's showing you know what probability you're looking for. The probability of what event? The probability what? What did you write in parentheses? That you roll an odd number. Not a 5, not a 3, not a 1, but all of those numbers, right? So what number, what value did you put in your numerator, Matthew? What value did you put? He put a 29. Well, where in the world did he get a 29? I don't see a 29 anywhere here in this table. Hadley?
He adds all the frequency of the odd numbers up.
Yes. If it says an odd number, that means 1 is acceptable. That means 3 is acceptable. That means 5 is acceptable. So how many tries for 1? What was the frequency? 10. Plus how many for a 3? 8 is 18. Plus 11, which is 29. Out of 50. And 29 divided by 50 gives me 58%. Okay? Now, I want to go back and talk about the likelihood. What is the likelihood that I would roll a 3? Unlikely. Unlikely. Remember, it's not impossible unless it's 0. So anything else would be either unlikely or highly unlikely. Okay, so unlikely. Now, this is not part of the problem, but it is on your quiz Wednesday, so I just wanted to give you a heads up on that. All right, what would you say about 58%? Likely or even equally likely? It's pretty close to 50%. Okay, so either likely or equally likely. I'm not going to be like overly strict on, no, you needed this exact word. But I want you to be close. If you said impossible for 58, or even if you said impossible for 16, that would not be correct. All right? So we have leeway, but you need to be close. Okay? All right, any questions so far? How are we doing on experimental? Doing okay? Favorable out of possible. All right, so theoretical. In theory, on paper, Nothing has actually happened. I'm just looking at what are my favorable outcomes and what are my possible outcomes, and I'm dividing them. So theoretical probability, let's look at this first example. It says you randomly choose one of the letters shown. What is the theoretical probability of choosing a vowel? Okay, so let me ask you this. If there were no vowels here in this red circle, what would you say the probability is? 0. Okay, so what I'm going to do is, what's my targeted outcome? Probability of what? Probability, and I would write vowel in parentheses. That's what I'm going for. So how many vowels are there in this set?
3.
There are 3 out of how many total tiles? 7 tiles. Okay, so for this one, it's not going to be an even percentage. That's okay. I'm going to round to the nearest percent. It's going to be approximately what percent? 42.9, or you could even just say 43%. Okay, I would give you instructions here that said round to the nearest percentage. If this comes up on your homework, you can round to the 10th or round to the whole. Both of the answers would be fine. All right, let's look at the next one. Choosing an X. Okay, so probability, something goes in parentheses, and then you have a fraction. So probability, I just put choose X. Choose X. If you said probability of X, that would be fine. If you said nothing, that's a problem. Okay, so probability that you would choose an X. How many X's are in the set? 1 divided by 7. So 1 divided by 7 rounded to the nearest percentage would be 14%. Approximately. That's the squiggly equal sign. Okay, that just means approximately 14%. All right, so let's describe the likelihood on these two. So 43%, how would you describe the likelihood? I would say closer to equally likely. You know, I wouldn't say unlikely. 43% is, you know. For 43%? Yeah, it's close to 50. It's closer to 50% than 25. Okay. What about 14%? Unlikely. Okay. So again, that's just if I were to ask you to describe likelihood. All right. So now let's compare the two. Let's compare the two types of probabilities. I hinted on this at the beginning of the lesson. And basically, what this example is trying to show us, okay, is as the number of trials increases, that the experimental, remember, I really have no control over the results of my experiments, right? Like when I'm spinning heads or tails, I could do 25 trials 3 separate times, and I'm going to get different results every time. You guys with me? Okay? So what it's saying is, I can't control those outcomes in experimental. It is what it is. But the more trials I have, the closer my percentage will be to my theoretical, which is, on paper, this is what it's supposed to be. All right? Okay? So in this example, experimental probability, I did leave out one key bit of information, rolling an odd number. Okay? So I'm looking for the experimental probability that I would roll an odd number. Okay, and that was from the book, and I missed that on your notes. So you do need to know, what are you going for? I could have said the experimental probability of a whole bunch of things from this table. So you need to know what you're going for, and it's an odd number here. So find the experimental probability based on the data from the bar graph, okay, of rolling an odd number. Now the last example kind of prepared us for what we need to do here to calculate our totals. Okay, so go ahead and try to come up with a fraction, and then you would convert that to a percentage. All right, let's work on that. So just on this brief walk around, I can see that there is a little bit of confusion between experimental and theoretical probabilities, okay? Experimental is actually what happened, okay? So we can pick out the odd numbers in this set, right? 1, 3, and 5 are the odd numbers. How many times did I roll a 1?
48.
48. How many times did I roll a 3?
50.
How many times for a 5?
49.
49. So on the experimental, it's how many times an odd number was actually rolled? 147. Divided by the total number of trials. But wait, the instructions don't tell me the total number of trials. Okay, you can add them all together. You can add them all together to get a total. Did you get 300?
Yeah.
Okay, so now 147 divided by 300, I can convert to a percentage. What would it be?
49%.
49%. And I can tell, actually, just by looking at this, 147 is pretty close to half of 300, isn't it? Okay, so now that's actually out of 300 trials. 300's a lot, isn't it? Okay. I've got this experimental probability. So let's see what's supposed to happen on paper. In theory, the probability that I would roll an odd number, okay, this is assuming that no trials have taken place. How many odd numbers are on the number cube? 3. How many numbers total are on the number cube? 6. Which is 1/2, which is how many percent? It's 50%. So what do we see here between the two probabilities? What do you see? They're pretty close together. While I can't swing the results to favor a certain way. I mean, literally, I just rolled it and recorded it. 48 times I rolled a 1. I didn't actually do it. It was from the book, okay? But somehow it still ended up being pretty close to the theoretical probability. So that's what we're saying. The more trials we have, the closer the two probabilities can be to each other, all right? Versus that first one, do you remember when it was supposed to be 50-50 and what was it? It was 24%. It was way off because there were only 25 trials. All right, are we getting kind of the gist of it? Okay. All right, one more example. A bag contains 50 marbles. 50, okay? You randomly draw a marble from the bag. You record it and replace it. The table shows the results after how many draws?
30.
So predict the number of red marbles that would be in the bag. Okay, so this is a prediction again. If you remember in the last example, in the last lesson, that last example, we used the relative frequency to predict a future amount. That's what we're going to do here. Okay, so probability that I would select what color? Red. Okay, I'm going to calculate it based on the information I have here. So what number would go in my numerator? Does everybody agree? 9. Out of, how many times did I draw? 30. Okay. All right. And I just need to change this to a percentage. 9 divided by 30. I could reduce it if you were to look in your book. Your book reduces it. It's not really necessary. You're going to get the same thing. Okay, 3/10, which is 30%, okay? 3/10, which is 30%. So what we did in the last section, which for consistency purposes, I think this is definitely the best way to go, use your formula. You're predicting now a future total. A equals P times W. You absolutely could use the proportion also. I just like the equation, okay? So what was my percentage? 30%. But do I plug in the percent? No, I need to plug in the decimal value. So A equals, if I know that it's 30%, the amount of red marbles is 30% of 30, I can use this to find 30% of 50. Okay? And 30% of 50 is how many marbles? How many would it be, guys? 15 marbles. 15 specifically red marbles. All right? So I use the percentage. Okay, so I find the percentage of what I had, and I use that percentage to predict the future. Okay, to predict a future amount. 15 red marbles. Okay, so let's look at this next one. It says an inspector randomly selects 200 pairs of jeans and finds 5 defective pairs. About how many pairs of jeans do you expect to be defective in a shipment of 5,000? So again, I'm going to calculate my, wait a second, would this be experimental probability or theoretical? They actually did this. They sifted through 200 pair of jeans and found 5 defective. So this isn't, well, hey, on paper, this should be the margin of, of error. No, they said this is what we found. So what am I looking for? The probability of what? The probability of what? Defective jeans. Probability that the jeans will be defective. So I'm going to use, okay, technically the word favorable is kind of like, you don't want them to be defective. But again, defective is my targeted, what I'm trying to measure. So how many were defective? How many were? There were 5 out of how many? Out of 200. Okay. So I'm going to calculate that percentage. What is the percentage of defective jeans among that sample? Okay. Are you guys getting 0.025? Yes. Which is 2.5%, right? Yes. But we're going to leave it a decimal. Why would I leave it a decimal? Yeah, because you would just change it right back to a decimal to plug it in to your formula, right? So if I know 2.5% of the trial amount were defective, I can use that to predict if 2.5% of this small number were defective, how much of this bigger order might be defective? Do you see how this could be helpful for a business? If they ordered 200 pairs of jeans and it came back 80% defective, do you think they're going to buy from this manufacturer? You think they're going to order 5,000 pairs to be made? No, because they're going to trash most of the order and they're going to lose all that money. So this is so important. Before a company will make a large purchase, they're going to do a trial run. They're going to see how well you make that product, right? That's what's happening here. Okay, so what is A equals 2.5%? What is 2.5% of 5,000? It's 0.025 times 5,000. Colin? 125 pairs of jeans. Okay, so let me ask you this. If you're the owner of the company, is this acceptable?
Yes.
Okay. If you could go to a different company and they could cut that number in half and make them for the same price, would you use the other company?
Yes.
Absolutely. But what if they charged you more money to make them? So these are the questions. These are the questions that these companies are asking, and people make full-time salaries to calculate this type of stuff. And to help them reduce these numbers, reduce the margins, okay, of defective products, and also to increase profit, ultimately just to make more money. Okay? How do we do on that, guys? All right, using experimental probability to predict a future amount. We're going to stop there for today. We'll do the last example tomorrow.